Okay, thank you very much. Yeah, for the invitation. Actually, this arithmetic properties of differential equations was my hobby for a long time, but yeah. I didn't really prove any theorems in this result, but formulated some conjectures, and we'll see some conjectures today. So usually we're interested in algebraic linear differential equations. Linear differential equations. In the case of one variable, and in the case of many variables, we say we get bundles with algebraic bundles with flat connections. Generally, get algebraic bundle, get smooth algebraic variety. Let's say number field. And we have algebraic vector bundle with flat connection. If you want to do calculations, you want to introduce some coordinates, yeah, and you reduce. What does mean coordinates? We choose some let's denote by d dimension of my algebraic variety. Choose d rational functions. Next, algebraically independent. And this rational functions gives you the following thing. You give, they will have defined on some the risky open part. And then you map by these functions map to d-dimensional space, maybe F, and then I can restrict. And this will be a tile map, yeah. So it's a ramified covering of some open domain, and then you restrict to U. And you get a vector bundle maybe in some larger rank on open domain, but still with flat connection. So you prime in a space, flat connection, larger rank, and you can trivialize your bundle. You get commuting differential operators. Trivialized bundle, again on using rational function, and we got commuting AIX are some matrices of some size with coefficients in rational functions of n variables. And finally, you have this number field. Number field has finite degree of rational numbers. You choose the base of your number field and consider the matrices with rational coefficients. Yeah, so eventually we can assume this Q. So you get rational values, rational functions, rational coefficients, and these things commute. And what is p curvature for this equation? Curvature for prime number p, which is very large. it should be sufficiently large so these denominators will not vanish mod p. In these things, what you do, you can make a reduction mod p. You get du dxi plus ai mod p x, where ai mod p belongs to, again, matrix valued functions. Now take rational functions with finite coefficients in my you get these things, and now raise this operator to p's power, or you can raise to p's power, consider it's mod p. I treat it not as something acting on a function, but like formal expression. So I get du dxi to power p, and now get new matrices, which called like p короче. They in general not vanish, and it's called p короче, components of p короче. Also belongs to the same p короче. And what happens, they commute. These matrices commute with each other. Sir? All the powers of derivatives disappear, yeah, mod p, yeah. Now, so it's a very elementary notion in coordinates. You just arrange these things to p's power and mod p, and so what is, and it was, I think it will be discussed on this conference, it's Grothendieck-Katz algebraicity conjecture. Then this matrix is VI, which depends on prime number p, yeah. It's all BIP equal to 0 for sufficiently large prime numbers. Then the conjecture is, in this case, a connection has regular singularities. Singularities is no exponential growth across singularities, and finite monodromia. And which is equivalent to the fact that all solutions are algebraic functions, all flat sections, and local flat sections over complex numbers, you see, are algebraic functions. Yeah. Which actually implies the following things. If you choose any base point xi0 in v to power d, where my connection has no poles, and consider a basis of flat sections near formal flat sections near this point. So we get so the basis consists of some series with rational coefficients, at informal variables xi minus xi0. Maybe to power n, because I have matrices of certain size n by n, yeah. And the claim that all Taylor coefficients belongs to Z, and you add inverse to some discriminant. So you have only finitely many prime numbers denominators. This is more stronger properties than vanishing of p curvature. This implies p curvature. Yeah, so it's, all these things should be equivalent. And this is very easy to check on computer, check and see that after rescaling, you don't see denominators at all in your solutions. Okay, yeah, so that is Algebraicity conjecture, and there is a Katz nilpotence conjecture, which is much more vague, I have to say, and have little chance to be provable at modern stage, because the other part has no good not really good definition. If for all sufficient large prime, all bi are nilpotent, this matrix valued functions are nilpotent, then maybe here I want to assume that a connection is irreducible. Yeah, totally sure. So I have a reducible connection. It's this property of nilpotent depends only on reducible components, because if you get extension, the matrix will be upper triangle extension. Yeah, so if all this guy are nilpotent, then this connection should be this bundle, this connection should be either direct summand of some Gauss-Manning connection coming from families of varieties. So you get homology of family of varieties, at least if you maybe. But this is something called Makiewicz local system. Yeah, there is something, some easy observable fact. It's kind of abstract story. We don't write formulas. It has regular singularities. So I didn't assume anything about singularities, and monodromy around ramification divisors. Ramification divisors are quasi-unipotent. So the finite power is unipotent operator. That's actually Katz proved this property. It's the only thing which is easy to prove. That's kind of true. But if it's come from geometry, there's a whole package of properties we expect that also monodromy should be defined over Q bar. And you should have a variation of pure Hort structures, and its case is reducible on the whole story. And because it's defined over Q bar, then you get defined over, you get for each prime L, for any prime L, you get QL bar local system this and you get representation, you should get a kind of semi-direct product to consider profiling completion of geometric fundamental group of maybe domain U prime and modular transrequisite Galois group of Q bar over Q. So you get arithmetic fundamental group acting here. So the things will be invariant under conjugation by Galois group of Q bar over Q acting on space of geometric representations. Yeah, that's kind of something which makes sense without speaking about families of varieties. Very often we don't have explicit formulas at all. Yeah, actually, it's about these situations when you have all elements of what you want like to have matrix system, but you don't have actual integral representations. There are numerous situations when we have. I don't know not about this one, don't know about this guy, but at least it's monodromy defined over Q bar, and equations also have algebraic numbers as a coefficient simultaneously without explicitly writing integral formula. So there are, what are situations? First, one can speak about hypergeometric, generalized hypergeometric functions, let's say in one variable. You can write equation, you can write monodromy. Why you can write monodromy? Because it's rigid. There's only one local system with given conjugacy classes. Yeah, so this is a property of rigidity. But also in integrable systems in mathematical physics, people have kind of a whole set of examples when I don't have yet integral representation, but we know that the monodromy is defined over Q bar. Not because of your local system is rigid, but it because you get usually local systems, something like configuration spaces for all braid groups, and they're compatible in some way. So you get something like braided categories. And then these braided categories are the same as rigid object. When you combine these things for different varieties, they interact in a certain way. And if you pick local parameters, like local eigenvalues monodromy, these things will be unique. Then they kind of a posteriori know they can control both monodromy and equation. It's kind of unique object for both description, but still there's no integral representations unknown. And kind of the example which I'd like to mention is something called Dunkel operators. You consider maybe gamma will be finite group generated by the complex reflections. I think it's reflections. Yeah, so you get plenty of hyperplanes when you put these reflections, and now consider some representation of group to ln C. And now you reflections in some vector space, and you get this plenty of hyperplanes, and you take d log of equation of hyperplane. And for this hyperplane, you do corresponding row of corresponding reflection. It will be a matrix, and we multiply by any constant, which will be a rational number. Consider, yeah, so we get matrix value at one form. It's flat, very easy to check, but I think for most parts of example, it's not clear how to get integral representation. Okay. Yeah, so now about this p-curvature conjecture, I want to offer some natural generalization. One can understand this conjecture from a slightly different perspective, what does mean this vanishing of nilpotence of p-curvature operators? Let's consider algebra of differential operators. And its usual relations. When I have my maybe meromorphic bundle, consider all sections as poles in where my form has poles. It will be a module over this algebra. Get module of these things. Which will be finitely generated. And if it's finitely generated, one can make a generation. One can make filtration. It will be 0, 1, 2. It will be generators. And now you apply, going to x6, you apply xi over d over xi. Go to next generation. So consider filtration by number of times you multiply generators in this form. So get filtration by finite dimensional space. Increasing filtration. Dimensional spaces. And this model which you produce in this way, it will be holonomic. You choose generators. You choose generators of your module, then apply, multiply by xi and d or dxi, you get next term of filtration. Okay. It's called Bernstein filtration. On differential operators of polynomial vector space, you treat all generators equally, like d or dx and x story, and then you can make generators over integers, and you can make these things over integers. Over z. And yeah, so use generators and generate like modules over integers instead of rational models. Get module over z. We gain increasing filtration. And what does it mean holonomic? Holonomic means that rank of m less than k grows of k to power d. A priori, it could be k to power 2d, because we have 2d generators. And holonomic, it's a minimal possible growth by Bernstein inequality. So instead of flat connections, one can more generally speak about holonomic D modules. Yes. And then here, what goes on? Now, if you make module over integers, you have a module over differential operators indices, you can make reduction mod p, and C6 has a huge center. And center is polynomials mod p with p's power of these guys and p's powers of these things. And now I put together this these things commute. It has huge center, and it has it's kind of a bundle of rank p to d, with d is number of generators, and it is bundle of it's Azumai algebra over center. So it's kind of bundle of twisted form of matrix algebras. So after some extension of scalars, you get actually a bundle of matrix algebras, twist form of matrix algebra of size p to power d and p to power d. Yeah, and what goes on? You have this D module. You can forget about action of the whole algebra. Consider action of the center. You get a coherent sheaf. Action of center only. You get finitely generated thing. You get coherent sheaf on a affine space of a finite field, Fp, with at most d-dimensional support. And this support I'll call it like P support of the module. It's an of characteristic variety. There is a not very difficult theorem by Thomas Bethune that this for P large enough, this P support is Lagrangian. It could be very singular, but if consider corresponding reduced variety, it will be pure d-dimensional and Lagrangian and generic point. Sure?
You had to choose generally.
It doesn't depend on choices.
So at the end, it doesn't depend.
Yeah, for large P, it doesn't depend. Yeah, okay. So we get this P support. So how geometrically Katz conjecture can be formulated? Nilpotence conjecture. Maybe you have this domain in AD where you have actual flat connection, this risky open domain, and consider only P support in a part in U prime cross AD kind of dual. It will be cotangent bundle to U prime. The Katz-Nilpotence conjecture says the following: if P support is zero section, it's eigenvalues of nilpotent matrices, then you get then it should be equivalent to the fact that you get motivic connection. And if you start to include, don't remove the Zariski open things. Like let's say do in one direction. You do kind of like a fine line minus finitely many points, and this P support will be horizontal line and many of cotangent fibers and various points. One can make some little experiment. Now consider irregular singularity. And in the case of irregular singularity, it's the most simplest case. You get exponential function of some polynomial. You get maybe some, I don't know, some rational function. Rational function, and then you write a connection. N will be 1, and my commuting operator will be d over dxi plus dif dxif. no, dxaf. Yeah. The flatness is obvious. And then one can calculate what is the p support. That graph of differential. So we have now like vertical coordinates, horizontal coordinates, and yi is equal to df xi. See the graph of you can see the graph of differential in the cotangent bundle. For large prime p. Yeah, so it's kind of similar situation. You kind of know p support for all prime p, but it will be no longer conical in vertical direction. It will be different one. It will be just general variety. Now I'm ready to formulate generalized Katz-nilpotence conjecture. So for holonomic d-module over M, or maybe say simple again to be on the safe ground, holonomic d-module M over Weyl algebra. If there exists closed Lagrangian subset, algebraic subset, such that for all p large enough, p support of M is contained in L mod p. It makes sense. You choose again some model. If for large p doesn't depends on choice of model, then it implies that model is exponential motivic. And what is the meaning of exponential motivic? It's very simple. There exists another model M tilde, which is motivic d-module on your actually it's on a fine space in x coordinate, yeah, but let's denote just by any variety x. And for any algebraic variety x, one can define what is algebraic motivic model as the following way. You have d-module on x cross a1 with some extra coordinate t, and with a property such that if you make projection get 0, such guys motivic holonomic d-module. It's the regular singularity. If you put these conditions, it's something called pair 0 in theory of exponential motives. They form a Abelian category, and it's simple object in this, and M tilde simple in this category. Simple in this category. Sorry. It's projection. It's like pi r. You consider because fibers are one-dimensional, you have only 2 zeros and first cohomology, but both of them should vanish. And object should be simple in this category. It's a abelian category, and how we get M? You consider M tilde multiplied by kind of exponent of T module and take direct image. Yeah. So in plain terms, you mean that you write integral form including exponent of algebraic functions, not only algebraic functions. Oh, it's tensor category. Yeah, it's everything. The tensor category can make Fourier transform. Yeah, it's. It will be tensoring bundles. You make addition in cotangent direction. Yeah. So it's a nice extension of usual motifs, but not verify. You see that it's just motifs on. Add one extra variable, and there are again some properties that it implies that M can have irregular singularities, but monodromy is still defined over Q bar, and Stokes filtration responsible for irregular singularity is also compatible with Stokes filtration. Is compatible with this Q-bar structure on constructible sheaf. Yeah, there's no nice things about elliptic representations, but there's again analog of Hodge filtration, blah, blah, blah. And also what immediately you see, you can have actual automatically rescaling. You can rescale variable t, so this thing automatically belongs to one parameter family. Yeah, opposite direction, it's kind of essentially explained because for exponential function we have graph, and then we can follow what goes on with support with when we make direct images. Yeah, so that's very nice conjecture. And here you see that's kind of like variables x and dx are completely equal. Yeah, so you don't really treat it as a differential equation. Sorry? No, between it just for any holonomic module. For any holonomic module, this P support is Lagrangian. It's whatever, arithmetic or non-arithmetic. But then this main story, these things can move. So in fact, what is going on? This kind of really fundamental observation. This when I do this calculation mod P, you get Lagrangian variety. It's defined by some equations, and degrees are uniformly bounded. They do not depend on prime number. And how one can see it? That the degree is uniformly bounded. Yeah, so actually what I mean by degree, if you get variety in affine space, you just intersect with affine space of generic affine space of complementary dimension. How many points? theoretic points you have. The idea is the following. If you get Lagrangian variety in affine space, which is kind of has symplectic vector space, you can do the following. You can produce from this you intersect planar curves, family of planar curves. You intersect with some coisotropic subspace. It's subspace which contains a Lagrangian. Then this subspace you mod out by AD minus 1, which is AD plus 1 square orthogonal. It projects to A2, which will be symplectic quotient. And then I get a curve. Maybe this coisotropic space will be generic, but transversally intersectical. So you get a curve in affine plane. That's what one can do with Lagrangian subsets. And the same thing one can do with D modules. This coisotropic subspace corresponds to very simple D modules. You can associate in this Hamiltonian reduction. Yeah, so this Hamiltonian reduction, it's like functor for D modules here to D modules here. And it will be given by some very simple explicit kernel, some Gaussian kernel. One can apply this to D models and get D models. So the thing's reduced to one dimension. Why this curve has the same degree? And here it's kind of really key basic calculation here is I'll do on clean blackboard this calculation. So this case of one variable, I claim it's really, please, it's the most important case. One can reduce to case of cyclic module because it's simple module, makes any generators. So consider some polynomial differential operator. X, okay. Get final polynomial differential operators. Then, for all prime number greater than 2, one can produce a new TP, which will be just polynomial in two variables, mod p, of the same degree. Namely, what you do, you look on this Azuma algebras and make their representations, and look at places where my operator is not invertible. Operator is not invertible, it means the determinant is not invertible. So to see, to bound the support, we need to see the vanishing of the determinant. And now we do the following. We consider some variable xi and add p by p matrix of this form, or a, that I plus another matrix. This matrix satisfies this commutator's identity matrix. Yeah, so it's completely six. It's determined by p matrix. And then it's a priori it belongs to polynomials in psi in eta. Yeah, because Cij will make sense for prime number big enough. But in fact, it belongs to polynomials in p power. can check derivative with respect to xi in it vanishes, so it should be depends on p's power. And then I can write some I don't know some Cij now p. Again, Aj will be the same inequality now. C to power pi or pj, and now denote x as c to power p. It will be this Tp. Now that's a definition. So produce planar curve of the same degree. Yeah, and that explains why this p support has the same degree. And this you can, yeah, you see that if you calculate these things in many variables, then I get something again depends on p powers of parameters. Like in many variables, consider like two variables, you take p square by p square operator. Then in this variables xi, whatever, you have polynomials of degree proportional to p square, but they depends on p power. But when you test with p power, again, you get very big degrees. But in case of one variable, you get kind of remarkable things goes to itself. So in sense, I want to consider things only in one variable for this game. And I get a remarkable map from like polynomials with some Newton polygon of coefficients. I get polynomials with the same Newton polygons mod p for each prime number. And this map, it's not one-to-one because these spaces have the same dimension, but it's not really one-to-one. For example, if your operator x over dx minus some rational number, when I calculate the 6, the corresponding t, then Tp will be x times y minus lambda minus p minus lambda, which is 0 for p greater than 2, so very large. So it gets kind of the same 6 independent on lambda. And it's kind of baby example of Katz conjecture. It's function x to power lambda. When lambda is rational, it's algebraic, it's motivic, it's algebraic function. But if, for example, if lambda is, I don't know, square root of 2, how to see that you get this problem? This operator, which you can consider here, will be something like this. You can see this operator. And when I calculate these things, I get x squared minus y squared and minus, so I get, I don't really remember the formula, but you don't get constant curve. It depends on the fact is to square root mod p prime number, not prime number. And by Tupadov density for half of prime numbers, you get wrong thing. If square root of 2 does not belong to fp, get not xy squared equal to 0. Get some little correction term. Sorry? Yeah. Yeah, it's actually thisCijp will be polynomials of degree p in original coefficients. Yeah. Sorry? From T, I get usual planar, usual commutative polynomials for each prime number. That's the point. Yeah. So no. It's still don't want to have break now. Or maybe I just want to go to little concrete. Yeah. Yeah, if you get a polynomial of kind of bounded degree in let's say 2 variables, if you want to calculate its coefficients, it's enough to calculate values of polynomials in sufficiently many points by Lagrange interpolation theorem. Yeah, so all this maybe just consider constant term. For example, consider value at 0. Yeah, value at 0, called the det p of my operator t will be this tp 0.00. It's the same as determinant. You don't put any corrections. By p matrix, ij, cij, I. And in order to calculate coefficients of polynomials, you calculate this determinants and then apply shifts by x and u dx by constant. Yeah, so what is going on is the following. I introduce some, I'm not really happy with notation, this poor man adels. Yeah, it will be the following things. It's product of prime numbers, z mod p, divided by direct sum of prime numbers, z mod p. It's like sequences of residues when ignore first finitely many things. It's a ring. It's contained a rational number. And then that pt belongs to this ring. And to check Katz's conjecture, you should have to check several instances of the fact that these guys are rational numbers. Actually, this sometimes that p belongs to rational numbers. And this exactly instances when we can see Katz's conjecture. I'll try to think these things. It's kind of like huge domains. It's kind of analog of complex numbers. Or in certain sense, it's something very uncountable because very big. And you see that differential equations produce elements of this the infinity. And we are looking on lucky situation when elements are rational numbers. And also algebraic geometry produce elements of this guy in without any families of varieties, just for individual varieties. If you have a smooth algebraic variety over Q, then I have whatever the RAM cohomology of X is finite dimensional space over Q. Consider RAM cohomology, and then for large prime numbers, we get a Frobenius map because we can have good reduction, and we get approximate map to one variety to itself, but it's in another cohomology. It's well defined. It's mapped from the RAM cohomology to RAM cohomology multiplied by p-adic numbers. Now, if you choose a basis, homology the RAM, and we get elements in maybe product of QP. Again, we ignore small prime numbers. Some of QPs. You get for large prime numbers, you get sequence of p-adic numbers. So what one can what you can, and in fact, if you choose the following happens, it's p-adic numbers, but one can control the p-adic valuations. If you choose basis compatible with Hodge filtration, basis compatible with Hodge filtration. Then this matrix will get columns divisible by appropriate power of prime numbers. Then I divide by matrix coefficients by appropriate power. It belongs to ZP. And then I consider leading digits. And these leading digits will be elements of the infinity. Yeah. In fact, there are further digits. Yeah. So what you get prime number 2, 3, 5, and can digit number 1, 0, 1, and you fill the whole table. Yeah. You got many or almost all table because it has many numbers. Each of them are digits. And people in periodic differential equations or periodic Hodge theory are really interested in kind of one prime number, and especially interested in cases we get better reduction, because the good reduction is kind of like baby case, and then looking on all this very complicated story. What I'm looking this direction, leading digits, but for large prime numbers. One can combine a little bit, think small. One can make for large prime numbers. Look for second digits, third digits, and so on. And,
not one element.
It's a matrix elements, yeah. And this matrix is invertible. If you divide by p digits, is determined is equal to 1 after you divide by power of p. Yeah, so it's all nice. Yeah. So you get something like periods here, yeah. One get things coming from algebraic geometry. You can make like analog of, for example, what is log 2? It's you do something like this. And so on and so forth. The square root of 2 go to 2p minus 1 over 2 mod p. So there are various things. One can go a little bit beyond algebraic geometry. We have Euler constant. It's exponential period, but then I get this guy. So in this ring one put analog of periods, and differential equations do something else. And originally when I kind of realized that when can calculate this criterion for that's what you do numerically for check Katz and Potts conjecture, calculate this p-determinants. And then I just started at random to feed my computer with operators. And then I see sometimes it leads to rational numbers, sometimes it depends on p modulo 24 or something like this. It's like Artin characters and so on. So I thought maybe they should come from algebraic geometry at the end of the day. But I think it's much larger class. It's the larger complex numbers will be like some coefficients of some monodromy or eigenvalues of monodromy metrics or stuff like this. It's not really periods. It's some completely different gadget. And now I show you some kind of numerical example which appears when I try to deform. Huh? Sorry? No, but no. Here you see, kind of ignore.
But you have none of.
No, see, it's really poor manner. I can ignore it's infinite prime as well. No. It's not. It's asymptotic information. It's not terribly precise. Okay. Yeah. So I take. Now, I at some point I ask myself, what happens if I perturb a little bit my operator when I have a control? What goes on in a small perturbation? I consider just some one-parameter family of operators, and operators which I consider was the following: it's du dx, x minus 1, minus t dx plus x. It's a Hohen operator. Hohen operator, and it's self-adjoint. What is t? I consider over q of maybe t, or is its projective limit of truncated polynomials? I consider t is an nilpotent variable with some big power equal to 0, like this. It's a small parameter. And let's calculate the following determinant. Again, by p matrix. Yeah, it's how it acts on truncated polynomials fp of x mod x to power p. It has basis. And I calculate how it acts here. It is a variable. And I get a really stupid simple matrix. I get this three-diagonal matrix, how it acts on operators, and I get a polynomial in fp of t. Then I can maybe truncate it. Look on this. What's commutative subalgebra? It's value of my polynomial at 0. When I consider cyclic module, it will be like family of get family of matrices depending on two parameters in mod p. And when these matrices are not invertible, then module is 0 at this point. Right? Looking where it's not 0, so it's no p by p. Because no, this algebra has rank p square, but it's dimension of p by p matrices. Okay, yeah, p squared will have two variables, but in one variable I have p by p matrix. Yeah, so I got this determinant and kind of observation, which is not a theorem. I'll explain why. There exists a series sum over ci ti in variable t from 0 to infinity such that ci belongs to zp for I less than p, and then this determinant is equal to the following things. It's sum over I from 0 to p minus 2, ci mod p times t to power I, minus t to power minus 1. Yeah, so you can calculate all these things, or if it using this one series, or if you truncate, you see that each coefficient stabilizes to rational number. Of course, if p is less than, it doesn't stabilize, you get 0, 0, then the residues of your number. And what are these numbers? Yeah, then I discovered it on computer. I just calculate maybe up mod to t to power 10, take this determinant, this coefficients, use, at the end of the day, use something like all 40,000 prime numbers, change the remaining series, and I calculated, I have a table up to 251, which took me several weeks some years ago to calculate, and it's 2 megabyte. Numbers are huge. It's the last number can something like 20 screens. Yeah. These are absolutely huge numbers. How they look like? you get like 0, 1, 2, 3, 4, 5, 6. The first two coefficients are 0. Then the first C2 is equal to 1 over 4 minus 1 over 24. And maybe I'll write number 7. Yeah, they look like all negative, 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 but C7 will be positive, so it's there was some. Something. The fact I kind of know, I have closed formula denominators. There's some simple, some strange closed formula which doesn't look like p-valuation of factorials. It's something very different. It's some strange guy. Yeah, so you see that series static is minus 1 over 4t square plus minus blah, blah, blah. So it's minus 1/2 t plus something squared, yeah. It's called maybe minus lambda t squared. And then there is a theorem with Sasha Desky, we proved a few years ago. First, we prove the theorem, when it's very difficult to analyze the proof, but the theorem says the following. We prove that this determinant of P by P matrix, modular T to P over 2, with all these half coefficients, is equal to sum over Ci Ti from P minus 2. So we didn't reach half of coefficients. I have really no idea how to prove it. It's numerically holds, but it's not part of the theorem. Yeah, so there's a series. And what is the meaning of the series? To describe lambda of t. In meaning of lambda of t, if t is complex numbers very, very small, then the sum of Ci Ti is convergent in C, and is equal to determinant of logarithm of monodromy matrix when you go around 2 points, 0 and x, 0 and t. You see that equation has 4 singular points, 0, t, 1, infinity, t equals, you can make for t small, this well-defined loop surrounding 2 points, and you consider general logarithm divided by 2 pi I. And algebraically, what does it mean if you consider this little annulus? In this annulus, you will have solution x to power plus minus lambda t, and some series of n, x to power n, depending on lambda. N belongs to integers. And this one can calculate symbolically. But again, my co-author is very good in computer. He tried to do kind of like, from this description, one can get some algorithm over rational numbers, how to get this number Cn. He was able to go maybe up to 40 coefficients. Then the memory was completely blown up of the computer. Yeah, so it's really very hard to calculate numbers. Rational numbers, very hard to calculate. Yeah, so there are kind of couple of, first I can say how to prove this theorem. We have very, very complicated proof, and it's like we didn't understand the proof. Yes, it was kind of formally worked, and referee checked it, said it's okay. I don't know how he checked because I tried to read our proof. Our paper is unreadable. Yeah, logic is extremely complicated. But recently I found really simple proof, and I will just explain to you right now. I don't know, no, but it's really new proof. No, there was some kind of basic ingredient what you do. You get this matrix. It's a part of big matrix. You consider I know this is your ring. Let's make truncate it. Maybe with integer coefficients. I take truncated polynomials in K and consider acting on Laurent series in X. As I have operator acting here and have basis consisting of integer powers. Yeah. And what here I can write matrix in general. It will be infinite matrix, like infinite by infinite matrix. And mod P, I just take a little minor of this matrix. But in general, I can make a minor. Now I can do the following. I can act on this guy, but also I can multiply by x to power epsilon. Epsilon is a kind of formal parameter. So what does it mean? When you get this something, you get some matrix coefficients. I don't know something like k square times the plus 1, and whatever it was, kk plus 1. Plus 1, you get this part of your things which is repeated, yeah? This matrix, you replace k by k plus epsilon. The matrix will be polynomial depending on epsilon. And get Bmn, mn, where m less than n, integers. It will be minor of this matrix when you consider powers of x to power n plus epsilon, where n. You consider only, you just cut rudely your matrix and get a minor. It's also subquotient. I don't do anything in characteristic P at all here. It's all rational numbers. And I get this determinant of this matrix. And what is it? It belongs to this, my little ring, yeah? And apply, and to get polynomial in epsilon. Get polynomial in epsilon. I better do it like this. So I consider polynomial, it will be polynomial of degree n minus m plus 1. Or something like this, yeah. No, it's polynomial of degree with twice this number. And it will be not really monic polynomial when t is equal to 0, we just truncate, consider the deformation of polynomial, all roots are integers in epsilon, are integers, because you get, when t is equal to 0, you get upper triangular matrix, and you get just epsilon plus 1, epsilon plus 2 is diagonal terms and so on. So you get epsilon plus, if you consider minus roots, you get the following thing. You get number m once, at n you get twice, and m plus 1 you get twice, and the same root, n plus 2 get again twice, and again get twice, and n plus 1 you get again once. Yeah, so it will be minus roots will be these integers with this multiplicity. Now you turn a little bit your parameter t. These roots start to move a little bit. When they move a little bit, there will be still which roots concentrated near each prime number. So you can make product of monic polynomials around integers and times some leading coefficients. And what you get this determinant of this matrix, Bmn. It will be leading coefficient, which we will calculate 1 over 1 minus t, multiplied by product of monic polynomials. Some kind of fi epsilon plus k. K is equal to m to n plus 1, it will be monic polynomial. The first one will be degree 1, but two of the boundary will be degree 1, the rest will be of degree 2. It will be epsilon square plus something for k strictly between m and n plus 1. It will be quadratic polynomial, and it will be leading term. And then if we look what is going on, and the whole thing is if you shift m and n, you just shift the same polynomial because the whole thing is covariant. Now, what happens when the sizes became large? If I, for I something less than k, the first k polynomials stabilize, last k polynomials also stabilize, but the middle, what goes in the middle with the same polynomial. And it's very easy to prove. You go to logarithm of matrix and calculate trace, you see the stabilization. So you see get kind of first k terms stabilized to something, it's called something FL, this F right piece, and then it gets the same polynomial in the middle, and what the claim is this function. This determinant of my minor will be constant term multiplied by FL of epsilon, maybe multiplied by F. It will be a product of all these shifted terms, FR of, or maybe epsilon plus M, multiplied by FR of epsilon plus N. Will be some two boundary terms, and then product of some monic polynomial, which is look like this. Omega epsilon is epsilon square minus 1 of. But I think I showed already this table. Yeah. So you see exactly epsilon square minus, and the constant term will be exactly things which I am going to. And product of this omega epsilon a plus k, where k is starting from m for certain omega m. K was degree of truncation, maybe omega epsilon plus n. N starting from m plus k, and n going to n minus k. So we got this formula. It's identity of polynomials. It's one can think, but now set epsilon equal to 0. When epsilon equal to 0, then this is my ring. Consider my ring, which is q of t modulo t to power k. This operator has no singularity at 0. It's preserved this subspace. So my matrix is block up low triangular. It preserves the subspace. And when I consider the minor, where m is kind of very negative and it's very positive, my product is equal to the product of two determinants. And now if I substitute, then I produce the following identity, that f left of 0, again, multiplied by this constant term, multiplied by f right of 0, because I get kind of left part here, it will be left part right here, one determinant, or you can consider the whole determinant, it will be product of a lot of w's, is equal to product of w n, for n going to from whatever minus b to a. We get this identity. Again, no prime numbers involved. And now Yeah, these polynomials automatically will have some denominators when control them. Not a big deal here. And then what one can do, one pick this prime number big enough, bigger than 2k, it turns out. It's the only things which there's a control. Then one gets this. What happens, you get left and right terms, but product of left and right terms mod p replaced by product of doubles, so you take product of doubles for all possible shifts. And then this guy is equal to W 0 mod p. Okay, yeah, that's essentially the proof. Yeah, so it's now became really understandable, at least I understand it. Now I want to say a little bit about some numerology. There's zero radius of convergence in QP p bigger than 2. Yeah, so it's an analytic function in complex numbers, but has zero radius of convergence periodically. And if you look of valuation of coefficients, you get like n, you get valuation of periodic valuation of Cn. You get not convex things, but very concave, p square, and so on. You get picture like this. It's completely experimental now. Just look from my data, I see what denominators is. This is a clear guess, and what it looks like. It looks like you get looks like Cn is equal to sum over alpha m divided beta m to power n. The alpha m beta n are periodic numbers, and valuation of the alpha m is m1 plus pm. It's a very small number. The valuation of p bm is m. It's bm is something like 1 over p to power m. But these guys are really very small, so all coefficients make sense. So it's like a function which has singularity. It's approaching family of things approaching to 0. It's not meromorphic function, but still has asymptotic expansion. 0, it has formal expansion, and it looks it has kind of well-defined values outside. Yeah, so one need kind of really to study it to see how one can calculate these values and what will be geometric meaning for terms of periodic differential equations. It's very interesting. It's kind of beyond the domain of convergence, but I claim that things exist in this strange way. And then one can try to calculate this like first B1. One can try to calculate, and essentially what we calculate the ratio of numbers, and using this 250 numbers which I have, I still not so many prime numbers to play. I still can say that B1 is roughly looks like minus 1 over p multiplied by some strange thing. Just using again Chinese remainder theorem. plus another term. Okay. And then it stops. In p to the power 6, the 6 doesn't live to rational number. Yeah, maybe I have a guess. It could be maybe this Mativik, some Mativik residue will appear, not rational number, something else. Yeah, one can. It's come from asymptotic C1 plus NCN for some n. If you look this position 6, you get this number. Instead we go Cn plus 2 over Cn, we get a little more. And I was succeeded to go up to p to the power 8, maybe the second, or maybe to p to the power. I get some huge, some strange series up to p to the power 7 with huge dimensions, but then up to p to the power 8, I really stop. It's even not look like depending on the residue, mod 4, whatever. It's a more complicated. Guys, I have really no idea where these things come from. It's a big challenge. And denominators of these numbers, again, behave very, very nice. I think denominator of k coefficients is something like 2 to the power k, 3 to 3 plus k minus 3, 5, 3 plus k minus 5, 3 plus k minus 7. You go up to you get positive powers. This will be formulas for the denominator of this new series, on which I have really no idea. Yeah. So that's that was this experimental result, and maybe just 10 minutes. I have something else I want to say. Now, so see that it really goes on. We have nice kind of like exponential Mativik operators T, just in one variable, such that I forgot my notation. This corresponding this TP is a reduction mod P of some another polynomial tilde belongs to xy. Yeah, so will be some in general. I have this Mativik situation when we have generalized Katz conjecture works. Yeah, I get matrices. I get matrices from which I control determinants. Yeah, if I control determinants, it looks that I can write denominators of inverse matrix. I consider inverse matrix as a rational function in variable. Yeah, so it looks that if I want to have this matrix, if I invert this matrix mod P, I get a rational function. I get matrix, P by P matrix, with coefficients will be Fp of x, y, and get inverse to this TT mod P. I get matrix with kind of where to write, and my guess, it's very informal, one can write explicit matrix itself explicitly in this case. This matrix in closed form, whatever it means, and then it will imply that you can calculate possible traces, so variation determinants will be determinant of original matrix plus some traces of inverse matrix multiplied by things. You can combine things, you get closed formula, so it means that you always coefficients of the series will be Mativik. This should come from by analogs of integrals. Yeah, so that's and should imply that when a perturb for any perturbation of Mativik operator, this determinant will be series with coefficients in Mativik part coming from algebraic geometry of the infinity. Yeah. So it's principle like now what here goes on. It's a different game. It's kind of more fine behavior for individual prime number. Yeah, and there is a analog of this whole story, which is much more pleasant to work with for q difference operators. Maybe I'll say the following. For usual differential operators, you get q of x du dx, yeah? Maybe contains, and then can make a reduction. Q contains z, or maybe z to 1 over some n, and then you can make reduction mod p. And reduction mod p, this algebra has a huge center, yeah, because it consists of p's power. Sorry, capital N. When consider concrete operators, it have some denominators, and you remove the denominators. Yeah. And for differential operators, I don't want to have analog of q, but I want to have analog of these rings. Analog of these rings will be you consider rational function, Pelenos and q, p inverse, and you allow all possible roots of 1. But it's kind of analog of q, and analog of prime. Now, this ring of integers, you have only finitely many roots of 1, and then get finite architecture things, and then analog of prime numbers. Analog of prime numbers, consider n prime for n prime bigger than n, and consider q will be a reduction to primitive n prime root. You get cyclotomic field instead of finite field. The algebra which you consider is the following. You consider polynomials whatever with these coefficients in x inverse, capital Y inverse, modular relations x y is equal to qyx. Yeah, instead of differential operators, and then at roots of 1, this thing has it will be Adzubai algebra with center, and you replace you consider, before I consider xi plus multiplication operator, now consider this operator, and another operator will be small y multiplied by cyclic permutation operator, and they satisfy the same conditions. So get family of matrix algebra, get the same story. One can formulate the notion of analog of Katz conjecture as a definition of motivic things in this world. It will be kind of nice q-difference equations, things coming like for quantum not polynomials and stuff like this. It's a different mathematics. It's not number theory, like motivic, kind of exponential motivic. In this world, it really doesn't make sense to speak about regular singularities. All singularities are irregular generically. Only exponential motivic things make sense, not motivic one. And exponential motivic are correspond roughly like not polynomials, quantum invariance. And there is the same story here goes on. For example, I have analog of my operator. Yeah. I have my operator, which was in differential case x dx x minus 1 x minus t d plus x. Together with the proof we have a very general class of operators. I just presented in simple case. It goes to the following way. It goes to y minus 1 to y minus 1. It's pretty ugly, but it's just expand the things and make obvious Q analogs. Yeah, I can make this ugly things, which when Q goes to 1, approximates my original operator. And here it should be the same story. Now I should have I leave the when I take determinant, it will be sum over Cn e to power n, but Cn belong to this. It will be analog of rational numbers, belong to this ring, but have more and more denominators, and then it have, if you consider it cyclotomic field, it would have like 0 radius of convergence. The same story, yeah, and will be similar things, but much easier to study because you don't need Chinese Riemann theory. You can see things on the face. Okay, thank you. Oh, no, I cannot. Yeah, it's. I didn't define, the world is much simpler in Q-different setting. There is one basic equation, 1 minus x minus y of some generator is equal to 0. You consider a cyclic model generated by this expression. You take, now add many variables, you take like, get many variables, you get a 2n-dimensional torus. Then I took n plus 1, like 2d dimensional torus, you get d variables. Now you go again Hamiltonian reduction, you go d plus 1 Lagrange coisotropic subtorus, make the same things, intersect, project, and get equation in one variable. Very complicated, depends on how you choose this coisotropic guy. And hypothetically, this will be all motivic things. Yeah, so it's much simpler. There's no things like algebraic geometry, algebraic varieties. It's encoded by some matrices with integer coefficients. But there are plenty of coincidences between such D models, and we don't understand how systematically understand the equivalence relation and what really goes on. Okay. Okay. Yeah, okay.